Hi, humans. Yes. All right. So, if we're all ready, I can start my talk. I'm Ju. Today, I'm going to talk about generics, and this is a generic Go talk by a very generic guy. So, some of you, I think, know me as the sort of primary author of Gonia, which is a family of libraries, Go libraries for doing deep learning in Go. I created Gonia simply because I was very upset with the way Theano was working. Yes, I was doing deep learning on the since before Theano was doing it in MATLAB, right? So Theano came and sort of revolutionized how deep learning is done. Then TensorFlow came, then PyTorch came, but I wrote Gonia because Theano sucked. And there's a good reason why I say Theano sucks, because when you do things in Python, it's not really very well typed. So I created Gonia. Gonia is a family of libraries. You can do your deep learning stuff in CUDA, you can do deep learning stuff on CPU, but the main things I'm going to talk about are these two libraries, Gonia and the tensor library. So the Gonia library itself is the library that handles the computational graph, and I'll explain what a computation graph is later. And the tensor library is a library that handles the values inside the graph. Okay. So for the past 3 or so years, while the world has exploded with LLMs, Gonia has sort of stayed relatively static and unchanging, and that's because I spent the last 3 years trying to genericize these couple of libraries. So today what I want to do is to share with you the story of how I did it and why it went so wrong. And by the end of it, right, I hope to leave you guys with at least 5 morals of the story. And I'll try to do it in such in a Socratic way. So I'll present a problem. I'll ask you what's the problem. I'll try to get you guys to solve it, and I'll show you what my solution was. Now, when we're exploring the solution space, there's plenty of solutions, and I've explored most of them. I'm just going to show a few of things I've tried. Again, apologies if this goes wrong for a bit long. I didn't have a lot of time. I just wrote this talk this morning. So if I had more time, this talk would be shorter. Right? So everyone knows what generics is? If not, here is a quick primer. So if you write a function, can you see my, oh, you can't see my mouse. If you write a function add t any, at runtime, if you have something like this, add 1, 2, it will generate a function called add int that generates a type, that takes a parameter int and int. And so all the t's here are replaced by this one, okay? And the thing in blue is what we call a constraint. So constraints of any means t can be of any data type. And you'll hear me say the word data type and types. The difference is very subtle. I don't expect to be able to have enough time to go through the difference between a data type and a type. But bear in mind that there is a difference between a data type and a type. So let's talk about a computation graph, right? If you've got an expression, a mathematical expression like this, z equals to 3x plus y, this is the sort of computation graph that you get. Follow so far? And this is important because all neural networks are pure mathematical functions. It's just mathematical functions. There's nothing magical about neural networks. There's nothing magical about GPT. Oh. Yeah, well, because you've got big data. Well, you know, if you've got billions of dollars to suck in the internet as your training pipeline, sure. But fundamentally, all neural networks, big or small, are just a bunch of equations. And here I've diluted the equations down to the absolute simplest forms. 3x plus y. So you can follow, right? So 3 times x, you get 3x, and then you plus y, you get z. Follow? So this is a graph. It's a computation graph. If you run this, you get z equals to 3x plus y.
So z should be a plus.
Yeah, it should be a plus. I'll show you what inside a node is, okay? So inside a node, inside each node, it's a name. In which case, z is the name. An operation, so that you can reconstruct the graph and the value that it actually computes. So 3x, for example, has an op of multiply, and then in the graph itself, you'll have like the left child and the right child, but we're not talking about a child, we're talking about what's in the node, and you'll compute the value if there is an x to compute. Follow so far? So why generics, right? Because, well, let's think about it. One of the things about the value thing is the value is an interface, right? You don't have to worry about what that interface actually does, and what add looks like this. So when you have a function that looks like this, people can often make mistakes. So you create an x that is of a float type, a float value, and a y that's of an int, and then you get an error. Wouldn't it be nice if your compiler can catch it for you? And so that's the main reason for me to move towards generics. And I've written a lot about generics. I've written, what, 12,000 words on generics, long before Go had generics. I explained why I built my own generic system on top of Go's generic system for Gonia. And so part of the project is to turn my generics into, to play well with Go's generics. Right? So when we talk about generics, let's ask the question, what can X and Y be? Any guesses? Yeah, that's correct. No, absolutely. And there is a term for it. It's called number-like. Anything that is number-like can fit into this, right? X and Y is number-likes. And when I say number-like, this was one of those things that gained a lot of attention when I said this in the GopherCon Singapore last year. Everyone came and said, wait, you mean you can build neural networks with rotations of triangles? Yes, you can build neural networks with rotations of triangles. As long as they're number-likes, as long as they've got add and multiply. And so here I've got it. Thanks, Mike.
I know a bit of standard framework. Does that mean that X and Y aren't be matrices?
No, they don't have to be matrices. They can be matrices. Yes, so not matrix, so you're jumping ahead. But on the side note, I want to jump in a bit on add. Yes. So for this purpose, we're going to say number-like is anything that you can add to and multiply to. We're not going to think about inverse and identity elements. If you're familiar with mathematics, you've got your rings, your monads, your magmas. We're just going to talk about add and multiply. Anything that you can have define a function of add, define a function of multiply, that's number-like. Okay? And you can build a neural network with just this, by the way. Anything that's number-like. So yes, you can build a neural network with rotations of a triangle. Things to think about. But add itself is something very interesting, right? So when we think about add, there are two types of add that I can think of, right? So the first type of add is like this. So you add a duration to a time, and you get a result of time back. And we call these type of things affine space types. Okay? So 10 o'clock plus 3 hours is 13 o'clock. Does that make sense? The duration is 3 hours. You're not adding the same thing. You're not adding the same unit of things, right? Or you can add a number-like thing to a number-like thing. So we're not going to talk about affine space types today because that opens a whole new can of worms. For this talk, I'm only going to focus on the second type of types, the addable types. So Go actually provides you a standard list of sort of addable types. Oh yeah, hang on. There you go. You've got your complex numbers there. But a note on complex numbers, right? So complex numbers, you can do addition and multiplication on complex numbers, but addition and multiplication on complex numbers are not necessarily what you expect. A complex number, 1 plus 2i, is just an array of two floats, 1 and 2, right? But we define add in such a way that it adds up nicely. We define multiply in such a way that when you multiply 1 plus 2i by itself, you square it, you get negative 3 plus 4i. If you don't know why this is the case, just square it and work out the algebra. Remembering that I squared is minus 1. So that's a complex number. And like I said, a complex number can be approximated. You can define your own complex number types by doing something like this, right? And so we can now generalize this to say that, well, what are number-like things? Number-like things are things that are a pure data type or a list of data type, a list of the T, right? Either T or a list of T. And if you've ever written a function that looks like this in Go, you know that this is actually very, very hard to actually manage, and you need a lot of funny any x dot type equals to blah. It's not easy to manage. So thankfully, mathematicians have a way to abstract all these things away, and we call the grouping of this and this together as one group of things is called a tensor. And that's what a tensor is. I'm actually there, but you know, you can nerd out that I'm actually, but basically what a tensor is a multi-dimensional array. That's it. What the multi-dimensional array represents is up to the person who defines what the tensor is. So if I define an array with two elements and two elements of floats, and I say that's a complex number, that is a tensor too. So how do you represent a tensor in Go? Well, this is a basic data structure to represent a tensor in Go. A tensor of any type has a shape, has a stripe, and the underlying data. Does that make sense? But of course, I have ADHD. So, monkey mind. The first thing I think about, okay, that was not good enough. That gives me a dense tensor. That means every element has to be filled. But when you do neural networks, there are occasions where you don't have to fill every number. Most of the matrix, most of the tensors are zeros. Only a few numbers are filled. So you create a type, a sparse tensor, a sparse CS is compressed sparse representation, or a coordinate representation. And then you might note that there's something new here, the engine. And let me explain why there's this engine thing in this definition. All of these tensor data types, tensor types, sorry, each of these tensor types have an engine in them. And the reason for having this engine is because when we talk about generics, it's not just one notion of generics. I wrote about this, right? I said 12,000 words. There are multiple ideas of what a generic is, right? So you've got something that's generic across data types, and you best represent this as something that looks like this. A container type that holds a data type, data of a particular data type. Does that make sense? So this container is generic across any data type, right? But it can also be generic across types. Here is where I get a bit interesting. So how do you define a set in Go? Here are three definitions of sets. So you've got a set, which is a comparable and a map to an empty struct, right? That's a basic set. You can also have a set that is defined by this interface. And this is a crazy set. This is actually there's a package called xtgo/set. The entire definition of set depends on the sort.interface, right? There's no additional data structure. This is an abstract data structure. So it's a type, right? You can create a set that is a small set. This is called a small set, usually. A small set of something is this. And then you've got generics across functionality. So can you tell me what's different between these two functions? The operator is different, exactly, and the default value is different. Now, some hoity-toity Haskell author would come on and say, hey, you can write something like this, You've got a fold left function, and you create your sum in terms of fold lefts. You create your prods in terms of fold left. You pass in the default value of 0 for sum, and you pass in the default value of 1, and you define mul, and guess what? That's not the same thing, okay? You can have compilers that compile these two set of codes to be the same as this, but they're not the same thing. The only way in Go to get this is to use code generator or macros, right? If you're into Lisp, if you're into other programming languages, macros are fantastic for doing these sort of things, right? And of course, you've got generics across computational substrate. So I want to run my expression on the GPU, or part of my expression on the GPU. I want to run part of my expression on my Raspberry Pi on the home network. And that's what I can do with the Gonia library. So I can have part of my neural network running on the GPU, part of my network running on my GPU, Raspberry Pi. Bad idea, by the way. Just to prove a point that you can have a network as a computation device. Totally bad idea. So this is the different type of notions of generics, right? So where did it all go wrong? So like I said, monkey mind, right? We talked about what the engine looked like. So what the role of the engine is to turn the dense and the CS and the COO into a pure container data type. And engines do the work. So you define an engine, the definition of an engine is this. It has no type parameters, yes? Okay, I can do that. Sorry, I am known to talk very fast, and when I'm not presenting, I'm actually talking at 3x speed. Sorry. Sorry? No, it is not being recorded. I will put up a recording on YouTube, okay? So you have an engine which has no data type, which has no type parameters, right? And then an adder is something that can add. An adder is an engine, but with an additional method of add. So so you can think of it as you can have a CUDA engine, so the engine that only adds using CUDA. You've got a CPU engine, you've got a network engine, you can write your own engines, right? So this is the fundamental reason for having an engine. And so now let's look at an implementation of an engine. So you've got the tensor, which is a the actual tensor interface is much bigger than this, but I've screwed it down, like truncated it to this. And you've got the dense, which we'll only be looking at from now on. And so you can see that dense implements the tensor data type, yeah? And so now let's implement engine. What's wrong with this? Can anyone tell me? Any idea what's wrong with this? Exactly, you do need the type parameter on the top. No, that was not a typo. So if you have a type parameter on this, then these need a type parameter too, right? And so that's the first moral of the story. If you add generics to your code, it's viral. It will spread into your code like a cancer, right? So what's wrong with this? Can anyone tell me that? So let's say we've implemented an engine that has adder, right? What's wrong with this code? Anyone? So let's read the data structure. An engine is type E that takes any data type, right? It's an empty data structure. But the point is that DT will be used later. So add takes a tensor of type DT, and then we range through the data and add the data. What's happening here? What will the compiler tell you?
Getting a type conflict.
Why? What sort of type conflict?
Yeah, two terms not really having the underlying operations.
That's correct. Absolutely correct. Any doesn't implement the plus type. Okay? So that doesn't work. So let's roll back a bit. What's the purpose of having the sort of dense data type, right? What's the purpose of having the dense type? The purpose is to be a container across the different data types and different computational substrates. I've managed to split up the purposes, right? Data type, computational substrate, right? So why can't I just do this? I make dense instead of any, I make the data types a float. Is this acceptable for most people? It is generic across two types of floats, right? But is this acceptable? Not for me. Yes, there will be a lot of monkey magic references. There were originally Go references, but I don't think anyone gets them. This is not acceptable, and there's a good reason why. In 2017, I gave a talk in GoFCon Singapore in which I gave an example of a programming language that uses natural language. So what you see here is you type what is 50 times 2, right? And it will generate a program, the LF, it's lambda calculus, which is the easiest internal representation to translate to other types, which is why I asked Simon earlier if it's a lambda calculus. So this is a lambda calculus, it computes the answer for you. But that table in the middle, it prints a bunch of numbers, but those are not actually numbers. The data type of those are cat spans, categorical spanners. So it looks at a particular sentence and figures out what category each span, meaning from what's the words what is 50, what is 50 times, what is 50 times 2. These are called spans. So that's basically a parser that takes in a cat spanner. And this is all done with the old version, where I made my own version of generics on top of the tensor. So it is actually very useful to have data types that are not just number-like, but any data type. So how do you constrain your tensor to particular addable or multipliable or number-like things? Well, remember what I said about the engine not having a type parameter? Well, engine has not a type parameter, so you create multiple engines. You create a default engine, which is for the basic standard engine for any kind. Then you create an addable type, you create a comparable type, you create ordinal types or ordered data type, and you create a number type and you order number types. So, for example, complex numbers fall into num, but not odd num, because you cannot sort a list of complex numbers, right? So yeah, so if you have this, then you have to do some really gnarly type switching. And this is the simplified version. The actual version has registries where you can register your own data type, and then when you create a new dense tensor, it'll actually use the correct engines.
Using reflection in those?
Yeah, some parts are using reflection, some parts are just hoping that the user actually registers a data type.
If you're going to extend your case statement dynamically.
Oh no, it's not actually a case statement. The case statement is just for this. It's just for this. It's actually a function call in which you reflect and figure things out, and check the registry whether a particular data type is available. I think I might have a slide in there about how I do it later. And then in order to do add, well, you check whether the engine is addable. If it's addable, then go, you can add. So the second lesson is that you should carefully constrain your data types. But if you cannot constrain it, or you don't want to constrain your data types, then you have to resort to ugly solutions like this. This is a really, really ugly solution, right? You've got an engine defined for each data type, and the ugly bit is like addable engine has embeds default engine, comparable engine also embeds default engine, and they embed each other. It gets really complicated. I ended up having to, I wrote a parser to parse my code to draw out the graphs of types. Oh yeah, that is also part of the solution. So that is part of the solution. Yeah, I got a bit greedy. I said, no, I don't want to just constrain it to floats. I don't want to just constrain it to the types that Go gives me. And the reason is because if you look at Olama, for example, they're not using float 64. They're using float 8s and float 16s. These data types do not exist in the standard in Go. These are special data types that happen to have add and multiply, right? So you want to be able to extend past what's already given. Sorry? What?
Can you speak?
Yes, you can big dot. You can use big dot int. Yes. So on that note, I'm also going to continue on the train of thought of being greedy, right? So this is the tensor interface that I defined earlier, but it's not enough for me. I blame Alex Stepanov for this because I've been very much. So in case you don't know who's Stepanov, he wrote a book called From Mathematics to Generic Programming. And he gave a very good explanation as to why you need what you need next. So I redefined the previously this was called tensor, now it's called basic. So basic is you can get the data type of it. But a tensor is something that you can clone and you can check equality of. This is the type of generics that people are not very used to. So you guys know to read this? No? Okay, so a tensor is a type, right, that takes of any data type, and it must be constrained where T has to implement basic. Okay? So when you clone, you get T back. When you check, you can check itself against another version of it, another value of the same type T. So if T is dense, you can check, and when you call the clone method, it will return a dense. It does not return an interface. It will return the actual concrete type itself, a value of that particular concrete type. So this is actual real Go code. So this is my new definition of tensor. The definition of tensor now is able to check for equality with itself, and is able to clone itself, and a few more, like it's able to create the same type but different data type. Like if you do a less than, right? If you do a tensor of less than A and B with a tensor of int in both of them, your result can be a bool, a tensor of bools. So it's able to generate something like that. But this is like the very basic interface that is minimally required. So if you're a type theory nerd, if you're a category theory nerd, yes. If you're a type theory nerd, if you're a category theory nerd, you've heard of REFL, REFL, reflective. So that's basically something that a 3-year-old once asked me, are all threes the same? Is this number 3 the same as this number 3? Is this concept of number 3 the same as this concept of number 3? And that is a surprisingly deep question, and that's why you have this equal requirements in here. Right. So as a result of that, your engine now has to have this. And you may be asking, why do you need to have an additional constraint for the engine, right? Well, consider add, right? The same function, we're just talking about addition, which is the most basic of all mathematics, right? Well, not really, there's successor, but you know.
Are those two t's the same t?
Ah, yes, yes, they are. So, so T must implement the tensor where this T implements basic. Yes, it's crazy.
Sorry, can you say that again?
So this T, right, must implement tensor dtt, okay? And what tensor dtt is that it must be of dt, of data type float 64 int or whatever, and it must implement basic.
So does that mean the t in the bottom of the tensor statement is like a subset of the t?
Yeah, that's correct.
But it has to still be of the same.
Right.
It's more constrained.
It is very, very constrained, yes. And so the reason why you need this is because when you think about add, right, if you give it A and B, you need to clone A and then return the results. And so to solve for the yellow question marks, you need to have a tensor that's clonable to itself, to its own data type. And that's why the engine needs this. Following so far? Cool. It's good to see that I'm not lost people. So, you know, create all these things, you create a whole bunch of functions, and thankfully I have a code generator that generates all this code for me. Thank goodness. And the result of greed, of course, is type parameters infiltrate everything, right? So if you recall from this is the original definition of node. Very nice, you've got op, you know, which is a function that takes a value, and now it looks like this. A node has you have to define what node is, and you have to define the structure that holds the value. So you can have a node that is of float 64 and a dense float 64, a float 64 and a sparse float 64, a float 64 and a scalar float 64. It becomes very, very constraining. It becomes too constricting, right? And so this was actually written, one of the first things that I wrote, which is greed gains you nothing, which is a Go proverb, board game Go, not the software, not the programming language Go. Greed gains you nothing. So after doing that, I talked about generating all the add and mul methods, right? So I got carried away. What's wrong with this? I gave a hint earlier. Can anyone figure out what's wrong?
Do you need to add more constraints to t?
Well, yeah, well, no, you don't have to add more constraints to t, but you are constraining everything by t. The engine is, yes, Miriam? Yes, it's too constrained. So it is too constrained, right? So if it
Too constrained, much too tightly ruled.
right, so look at this, right? E is very constrained. The engine type is tied to the data structure now, whereas it should be free. So if you create an engine and you say you want to create a dense, right? Sure, with this engine you create a sparse with this engine as well, and then you add it together, it will fail because the engine only expects dense tensors to add together, right? So if T is dense, when you pass in B and B is not a dense, B is a CS, it fails. It will not compile. And this is not what you want when you have a computational graph, because your variables can be of any type. Your variables can have any structure, right? They are tensors, but how the actual tensors are being represented can be anything, right? So let's think about it a bit more. Is T really necessary? If you don't think your way through, you spend 2 years figuring these things out, right? And you think about it, is T really necessary? What happens if you do this? So ignore the T for now, but you take a basic instead. Would this work as well as this? Right? So to help you go through this, let's look at how the actual methods are actually done. So add is very simple. You check whether the add is an adder, and inside the engine, you take a ABC and you iterate through them. Iter3 is an iterator, and you get the index for each I, J, K, and an error. This should be E, but you know, if you get an I, J, and K, then you can update the indexes like this. This is an iterator. The iterator doesn't care what data type it is, right? The iterator will work on a compressed, on a sparse data type when it's supposed to be a 0, when it's a not known tensor. Like let's say you've got a 3-3. Let's say you've got a 3-3 matrix, right? 3 rows, 3 columns, and only the diagonals are filled, right? The rest are zeros. So you have a list of only 3 numbers. That's a compressed, a sparse tensor. So when it goes to 1, 1, which is 0, 1, the coordinate 0, 1, it's a 0, right? The iterator will return a 0. So it doesn't really need the actual data type itself. It doesn't need to know about the data type itself. But over here, I was thinking, yeah, sure, it does. You have fewer calls to, runtime.assert I to I, runtime.conv I to I, runtime I to T. That's fine. It should be run. It should run faster. So for 2 years, I labored on this thing. I figured out a bunch of methods on this thing, and then I asked myself this question. Finally, asked, is it really better? And so I did a benchmark. I wrote the specialized one version is where the data type is T. This is the specialized version, and this is the standard version. And guess what? There's no difference. In fact, if you I mean, it's not statistically significant, but the specialized version, the T version, is actually slower than the interface version. That's crazy, isn't it? And I replicated this this benchmark for all the major sort of methods, and they all came back similar. There's no difference in terms of performance between calling an interface and passing in an interface type or passing in a concrete type. So, moral of the story: validate your hypothesis before getting away. Okay, the next slide, and the next slide is supposed to be hidden, but the point is.
Sorry, just a quick question.
Yes.
How would you validate that without going through pain?
Yeah. Well, sit down and think before you do it. The whole point of this fellow is that this guy doesn't think, right? He just does it. He just does the work. Sandy just does the work. He doesn't think, right? It's up to Monkey to think. Monkey to make a plan. You guys are too young for monkey magic. Damn it! Really too young. Sorry. Yes.
Are you insinuating that means you?
Yes, I'm insinuating that all the vices are me. I'm the sloth, the pig. I'm Sandy. I'm Pixie. I'm Monkey.
Did you do this for efficiency, or did you do this for code progression?
I did it for efficiency because I assumed. I didn't think it through. Run the benchmark.
It doesn't stencil it, and it's effectively generic. It's effectively useless anyway.
Yep, there you go. You figured it out. But that took me 2 years to figure out the stenciling bit.
He's smarter than you.
Yeah, Mark is smart. Of course, Mark is smarter than me. That's why he works at Google. So this slide and the next slide are supposed to be removed. But Go has a bit of expressivity problem. You can't say I want you to be the same type as T, but with a different DT in it. These things are called higher candidate types. And so I went down a 1.5-year journey, spitting on John Reynolds' grave. If you are into like functional programming, you know who John C. Reynolds is. He introduced the concept of defunctionalization. Defunctionalization takes higher order functions and turns them into lower order functions. And you can take higher candidate types, because higher candidate types are also functions. You can turn them into lower candidate functions. And there's a bit here that's like 15 slides on this, which is why I removed it. It's a whole lecture on itself on how to do really, really crazy shit with higher candidate types in Go.
Can you do it?
Yes. But then what happens is you have to think about the API, right? If you think about add, right? Add right now. Let's add. That's the for function add.
Do you end up in like things where you
Okay, if you look at add right now, if you pass this in right now, you just call add normally, it should work without having to pass in the type parameter. But if you do the higher candidate type stuff, you have to pass in the type parameter and say instantiate this add for this particular type parameters, which makes the user interface absolutely shit.
It doesn't like an interface with type operable, but like a thing can have an operation and then you define like an operation.
Funny you say that because operable is exactly the word I used. Okay, operable is actually literally the word I used. Okay, and then finally there's this. Take some time to have a look at this error. This is ridiculous. Sorry. Yes, I tweeted this. I tweeted this because what the what the hell is happening here? So to understand what this actually is, right? How in the world does the Go? This is the latest version of Go. It still gives this error.
Are they different things or are they the same?
They are the same. Sorry. So to us humans, we know that there's the same T, but to the thing is not the same T. All right. So I'll explain how we got there. So the crux of this function is this: I'm trying to create an operation, and this is the line. What's wrong with this line? So this is I'm going to highlight with this. What's wrong with this? So when you are stuck with this sort of things, here's a very good way to work through the problem. Again, this is written when much of this talk was tied up in Go parables, like Go the board game parables. Okay, so let's read. The important thing to do is to be able to read this. So what is the type of VS0? T. What's T? T is anything that is constrained by values.value. Follow so far? And what is values.value? Values.value is that one, right? So values.value is this one. It's just basically the same thing as tensor.basic, right? Does values.value have the shadow clone or clone method? It doesn't have a shadow clone method. So this will fail its compilation straight away. So how do you fix this? Well, you turn it into an any, and then you assert that it's a tensor.shadowCloner. And then you call values.shadowClone, which is this function. But when you do this, well, you get that error. What's happening here? Well,
Is that a bug in the way that Go does type assertions?
no.
Is it trying to...
At first I thought it was that. And this was the line that caused that error. The bug is very, very subtle, very insidious. Okay, let's read. What's the type of, after you've done it, what's the type of this expression?
Something that doesn't exist yet.
It's because you're trying to convert any into the shadow cloner.
No, what is the type of that red expression? What is shadow cloner T? It's an interface, isn't it? Okay? So the type of this is tensor.shadowCloner T. And what does that mean? What does the Go compiler do when you say this is okay, fine, this is type of shadowCloner T, and you instantiate shadowCloner. ShadowCloner is defined. Yeah. Ha! You got it. So when you instantiate, you're instantiating this function, which means you're getting this function. Okay? A shadowCloner T, shadowCloner, right? We replace this. We replace this T with tensor.shadowCloner. Okay? What do you want? You want this. You want a shadow clone T, not tensor.shadowCloner T. Okay? You want this function. So basically, we're confusing I switched up the slides. Here, on top.
No. You still don't have the definition on screen of shadow cloner.
Oh, shadow cloner is just an interface with the function shadow cloner of T that returns T. I didn't read. No, okay. That's my bad. I should put it there. But type of shadow cloner is basically an interface that returns T. Interface with a shadow clone method that returns T.
So can you just like find a certain shadow cloner?
Yep.
Does that solve it?
It solves the bug, right? Sorry. So the correct thing to do is, as what Mike says, you assert into a shadow cloner and then you call shadow clone immediately. You don't need this function at all. You don't need to call this function, and calling this function causes all these other errors. The wisdom is knowing when to do that. Okay? Again, this is a case of being carried away. I'm like, I've got a values package. All the values go through that package regardless. And there you go. That you end up with cases like this. So rules that are too general, well, they are too general occasionally when you don't have the ability to assert that T has a shallow cloning method. Yes. Yes. In fact, I'm suggesting like if this were the error, right? If this were the error, much of this issue would have been solved. This took me a couple of days to figure out, on and off, not constantly 2 days, but a couple of days. I was checking the commits to see how long it took me to fix it. This particular guy took. Yes.
Do you, like, is there a particular thing that, for want of a better word, is generic to all types of this error that you could upstream and say, look, if you're actually doing this sort of thing with generic,
You're not supposed to be doing this type of things.
More information, like more informational error message out of it, like that the actual compiler could go, hey, yeah, like we want that, but by the way, generic stuff. So maybe looking into this as well.
Yeah, I should probably compile. I have a lot of these things, right? I've got like 2-3 years worth of error messages that I went through.
Someone else is going to hit this problem.
Yes, someone else will hit this problem. And the root cause, as Miriam says, is to have better notation. The root cause is because the interface and your constraints share the same exact syntax, right? You wouldn't write this, would you? You wouldn't write this function? No. If you're going to write this function, you're going to be forced to write the type signatures that are constrained by it. Yeah? And this is the dangerous bit, right? Because you might accidentally, what satisfies T? The actual concrete definition itself and the interface definition, both of them satisfy the definition of T. And so if you instantiate the wrong T, if you instantiate the interface version of T as opposed to the concrete version of T, whoops. So the lesson here is to, at least mentally, you need to make clear what is a constraint and what is an interface. I try not to write functions in which I mean it as constraint type. T is a constraint type, right? T has to be this particular type. I try to make it so that it will never ever be a interface type. But it's not always possible, as you can see. So in conclusion, I talked about 4 sort of general patterns to doing things. And the sort of Zen way forwards is when you have generics across data types, use type parameters, use generics, use Go is generics. When you need your things to be generic across different types, Go already has that function. It's called interface. The functionality is there. Just use interfaces, right? And when you need to have generics across your functionality, well, use macros. And if you need generics across computational substrates, have fun. That's the end. Thank you. Are there any questions? Any other questions? No? Cool. Yes.
Generally, do like what makes it and use Go over strongly type languages as Go as Rust? Wouldn't that be like?
I don't like Rust because I have to fight the compiler all the time. I prefer Haskell, right? I code in Haskell, I code in Coq. Not a problem.
Haskell allocates everything on the heap.
Yeah. So
Rust allocates everything on the stack.
yeah, so those are like the issues that when ideals clash with reality. I code in Haskell. So most of these things, I have a Haskell sort of proof. I wrote the proof down in Haskell or Coq somewhere, and then I write the Go code before going on to write. Before actually writing Go, I would have proved it in Coq. I would have proved it in, well, not really proved it in Haskell, but at least on a sketch basis, I would have shown that, okay, this concept works in Haskell. I also would have sketched out a variance in C++ before going down exploring these things. So that's what took me 3 years. And it's still not complete. It's nearly complete. If you want to help, talk to me.
Are you planning on looking at type parameters and directions and Go? This is a fairly extreme use case.
Yeah.
Those who get nowhere near this is actually quite easy.
Yeah, exactly. So I have a 3-layered Yes, you can have 3-layer type type parameters. Which is why I say you give me any type system, I'll try to break it, right? When I got the 3 layers of type parameters, I realized that so this is 2 layers, right? So this is 2 layers.
We see quite a bit of the two-layered stuff in even the stuff that's in library.
So this is a 2-layer tensor. I actually got a 3-layer version. By the time I got to the 3-layer, that's when I realized, oh, that's gone too far. I've got to pull back. Because I wrote an API, I keep having an API, sort of the package level API to see how usable it is. The 2-level version is not very usable. The 3-level version is crazy. So the inferer is not actually able to infer. If you give it an interface type that has a concrete type of particular type, it's not actually able to infer all the constraints all the way. But hey, Hindley-Milner is actually a very easy way to write a constraint system. If you want to check out a Hindley-Milner type system written in Go, I have a package called HM, Chewxy/HM on GitHub. Like 400 lines of code, all type systems are able to be inferred. No need for set solvers. Yes.
So this is just for the presentation. Others like also you have just one presentation, right? You also modified the Go compiler.
I did not modify the Go compiler. 5 years ago when I had a lot more time, yes, I did that. Now I'm much older. Yeah, so I don't have any time to type anymore. So no more messing around with things like that. So, which is another reason why it's taking so long. Any other questions? Cool. Thank you for your time. This was a real weird rant.